In this mini lecture, we're going to talk a little bit about the fundamental theorem of calculus. I'm not going to present an actual proof that this theorem is true. I'm going to give some justification that makes it seem reasonable that this is true. You can find the actual proof of this theorem if you even just do a search on YouTube for the fundamental theorem of calculus proof. You can find a variety of videos that go through that actual proof. I'm going to approach this more from an informal point of view in this mini lecture. So to start with, we're going to think about a couple areas here. So we're going to look at the area under the graph of this function f of x equals 2x plus 1 for x coordinates between 1 and 3. And that's what I've got graphed here. So this is my function, oops, yeah, that's not what I want. This is my function here then, f of x equals 2x plus 1. Notice if you put 0 in for x, you get 1 out for y. If I put 1 in for x, I get 3, and so on. So if I want to find the area under this curve, one way we could of course do that is to just do it geometrically. And so, you know, I've got this, I've sort of got part 1 here and part 2. For part 1, that's just a rectangle. So the area is just going to be length times width. And it's, you know, if I just look at this, it's 3 squares up and 2 squares over. So that would just be 3 times 2, which would be 6. For area 2, that's a triangle. So the area would just be 1/2 base times height. The base of this triangle is 2, the height is 4. And so that's equal to 4. So my total is 6 plus 4, or 10. Okay. So again, the rectangle, we've got 2 by 3. 2 times 3 is an area of 6. For the triangle, 2 times 4 would be 8, but it's half base times height. Half of 8 is 4. 6 plus 4 is 10. Now another way we can find this area is actually using something called the antiderivative. And so the antiderivative is sort of what you'd expect. It's the opposite of the derivative. So if we have a function here, this function 2x plus 1, it turns out the antiderivative is going to be this function capital F of x, x squared plus x. Now to check that, notice I could just say then, what's the derivative of f of x? So what happens if I take the derivative of that function? Well, the derivative of x squared, I would just bring that 2 down in front, so that would be 2x. And the derivative of plus x, well, the derivative of x is just 1. So notice I really do have the antiderivative. If I take the derivative of this antiderivative, I get back to the original function. And now what I want to look at, what happens if I take capital F of 3 minus capital F of 1? Well, remember, capital F is up here, that's x squared plus x. So I plug in 3, I get 3 squared plus 3. And then I plug 1 in, I get 1 squared plus 1. So 3 squared, 9 plus 3 is 12. 1 plus 1 is 2. 12 minus 2 is 10. The same answer we got in part 1. Now, I've got another function here, g of x. So this is my function g of x equals negative x plus 4. And again, we can check to see that that is the valid graph. I'm just going to do this for x coordinates between 2 and 4. The geometric area, well, this is even easier as far as that's concerned. I just have one area here, it's just a triangle. The area would be 1/2 base times height. Well, this triangle is just 2 across and 2 up, so the base and height are both 2. So 1/2 times 2 times 2, 1/2 times 4 would be an area of 2. What about the antiderivative of this function? Well, to get a derivative that's equal to x, I'm going to have to start with x squared. But if I would bring that 2 down in front, I would need 2 times something to be this negative 1. So that's why I've got a negative 1/2 here. If I take this derivative, remember then, yeah, I would get the negative 1/2, and then I'd bring down the 2, the x would stay the same, and then the derivative of 4x is just 4, and then the negative 1/2 times the 2, that cancels. So I do get the negative x plus 4. That is a derivative then that matches up with the original function. So I really did find an antiderivative here. So I'm going to plug then 4 into this antiderivative and then 2 into this antiderivative and subtract. So if I plug in 4, I get negative 1/2 times 4 squared plus 4 times 4. Right? I'm just plugging 4 in for x up here. Now I do the same thing with 2. So I get 1/2 times 2 squared plus 4 times 2. So what do I get in the first set of parentheses? Negative 1/2, I forgot there. So negative 1/2 times 4 squared. 4 squared is 16. Negative a half times 16 will be negative 8 plus 16. Negative a half times 2 squared. Right? So here, 2 squared is 4. Negative a half times 4 would be negative 2. 4 plus 2 is 8. So negative 8 plus 16 gives me 8. Negative 2 plus 8 gives me 6. 8 minus 6 is 2. So again, this isn't a proof that this works, but this is what the fundamental theorem of calculus says, at least one form of the fundamental theorem of calculus. So I've got a function f of x that's continuous on the closed interval from a to b. And I have some other function, capital F of x, that's an antiderivative. Now, one thing here, I don't want that prime. Okay, no prime there. All right, so I've just got a capital F of x that's an antiderivative. Then, this integral from a to b f of x, I just take that antiderivative, like the capital F we had up here, the capital G we had up here, and I just plug in the upper limit and the lower limit, and I subtract. That's all I do to get the value of this definite integral. So, the fundamental theorem of calculus says we can evaluate the definite integral of a function by evaluating an antiderivative of the function at the two endpoints and then subtracting the results. So it's really important that we're able to find antiderivatives. So I'm going to keep this convention here. So if I have a function capital R of x, we assume that's the antiderivative of little r of x. Or in other words, if I take capital R prime of x, that's equal to little r of x, right? So some basic stuff here. Typo, that's number 4. So first of all, constant multiples. If I have a function c times little f of x and I want to take the antiderivative, this constant c sort of just goes along for the ride. The antiderivative of little f is capital F. If I'm adding or subtracting functions, their antiderivatives just get added or subtracted. If I take an antiderivative of just a constant c, that's c times x, I can see if I go backwards, what's the derivative of c times x? The derivative of c times x is c, so the antiderivative of c would be c times x. And then finally, the power rule, the antiderivative of x to the n, well, antiderivative is going backwards, so that exponent, when we take the derivative, it goes down 1. So if I'm taking the antiderivative, it goes up 1. But then I would have to bring that down when I would take the derivative, and I didn't have anything in front, so I have to put the new exponent in the denominator. The one thing, this is only valid if n is not negative 1. If n is negative 1, I would get 0 in the denominator, and that wouldn't be allowed. If I have x to the negative 1, that's really just then the function f of x equals 1 over x. Its antiderivative is special, and that's something we're not going to deal with in this course, actually. That'll be in Calc 2. So, as an example, let's just find an antiderivative of this function here. Okay, so my antiderivative might be capital F of x. So I've got 4 times x cubed. So that's a constant times a function. So my antiderivative is just going to be 4 times the derivative of x cubed. Well, to get the derivative of x cubed, I would have to increase that exponent by 1, right? So the antiderivative of x cubed, I'm going to have to make that go up 1. So that would be x to the 4th. But then I would have to divide by that new exponent. Same thing here then. The 2 would go along for the ride. The x squared, I would increase the exponent by 1 and divide by the new exponent. And then the antiderivative of 3 is just 3x. So these will cancel out. So I just get x to the 4th minus 2/3 x to the 3rd plus 3x. How do I check that? Well, to check it, we're saying this is the antiderivative. So if I take the derivative of this, I should go back to that original function. So what's f prime of x? I bring down the 4. I bring down the 3 and decrease the exponent by 1. The derivative of 3x is just 3. What I see here, these 3's cancel out. And so I get 4x to the 3rd minus 2x squared plus 3, which is the same function that I started with here. So this process really worked. These rules seem appropriate. Antiderivatives for trigonometric functions come directly from the derivative rules. So this table summarizes the basic antiderivatives. Remember, if I take the derivative of capital F, I get little f. Okay. So if I'm going from left to right, that's the antiderivative. If I would go from right to left, that would be the derivative. And so these rules here are the ones we just talked about, right? If I've got c times a little function f, the antiderivative, the c just goes along for the ride. If we're adding or subtracting, we just add or subtract antiderivatives. The antiderivative of a constant is just a constant times x. The antiderivative of x to the n is x to the n over n plus 1. Again, notice I can check by going backwards. If I took the derivative of this, the n plus 1 would have to come down in front. That would cancel. I'd subtract 1, and I just get back to x to the n. Now, these results, we can sort of think of these are just forms, really, of the derivatives. Remember we learned the derivative of the sine is just cosine, so that means the antiderivative of cosine is just sine. The derivative of cosine was negative sine, but there's no negative here. So if I want the antiderivative of sine, it becomes negative cosine. Same thing here then, the derivative of tangent was secant squared if I go from right to left, but that means then the antiderivative of secant squared would be tangent. Cotangent, its derivative was negative cosecant squared. So if there's not a negative here, we have to put one in with a cotangent. And then secant and cosecant work similarly. As a note, there are really infinitely many antiderivatives for any given function. This is because the derivative of a constant equals 0, so that an arbitrary constant can be added to any antiderivative to get a new antiderivative. So for instance here, we've got 4 functions, capital F, capital G, capital H, capital J. What happens if I take all of their derivatives? Well, f prime, capital F prime, if the derivative of x squared, I would just bring down the 2, and that would be 2x. What about G? Well, what's the derivative of x squared plus 3? The derivative of x squared is still 2x, but the derivative of 3 is 0. Same thing with H, x squared minus 4. Well, the derivative of that 4 is 0, so I still get 2x. So in general, we say x squared plus some arbitrary constant c. And that derivative is just 2x. So this general arbitrary constant c is often called the constant of integration. However, when we're evaluating a definite integral, we do not need to include this arbitrary constant, as we can see in the next example. There will be a time when we do what are called indefinite integrals that constant is going to be needed, but not when we're doing definite integrals, as this example will show. So evaluate this integral below, including the arbitrary constant c and the antiderivative. So to evaluate this antiderivative, this is my function f of x what we need then is my antiderivative, capital F of x. So how do I take the antiderivative of this? Well, the antiderivative of x squared, I would have to increase that exponent by 1. So I'd go up to a new exponent of 3, but then I would have to divide by that new exponent. Same thing with the second term. It's really 8x to the first, so it's going to become 8x to the second, but I'm going to have to divide by that new exponent. And then the antiderivative of a constant, well, that's just going to be 3x. And how I indicate then this business that I'm going to have to plug in the 4 for x and then 1 for x, we sort of put a bracket here and just put those limits down. So we say that means we're taking this expression and evaluating it between 1 and 4. Of course, we could simplify 6 over 3 is 2. Oh, and I forgot my c. That was the whole point of this. So my arbitrary constant, I could have a plus c, and I could evaluate between 1 and 4. Remember, those are x values, though. Now, 6 over 3 is 2. 8 over 2 is 4. So I plug 4 in for x. And then I plug in 1 for x. And so I get 2 times 64 minus 4 times 16 plus 12 plus c minus 2 times 1 minus 4 times 1 plus 3 plus c. So I get 128 minus 64 plus 12 plus c minus 2 minus 4 plus 3 plus c. So 64 plus 12, I get 76 plus c minus 2 minus 4, negative 2 plus 3, I get 1 plus c. So I get 76 plus c minus 1 minus c. The c's cancel out. And if you think about that a little bit, that's always going to happen when I'm evaluating a definite integral like this. The constant's always going to be part of the first evaluation and part of the second evaluation, but there's always a minus in between. So when I end up distributing that minus, this arbitrary constant c will always cancel out. So when I'm doing a definite integral, I really don't have to worry about that arbitrary constant.